When an automated machine carries a payload through an unpredictable physical environment, it relies on a control system to stay on target. The simplest approach to this is open-loop control. In an open-loop configuration, the computer calculates a control input based entirely on a mathematical model of the hardware and dispatches that command without ever measuring the actual physical output. In reality, the mathematical model never perfectly matches the physical hardware. Motors wear down over time, mass changes, and external disturbances like wind gusts act on the system in real time. Open-loop control is mathematically elegant, but physically fragile. Because it cannot measure its own output, it cannot correct its own deviations. A robust system requires an architecture capable of reacting to its own errors. This closed-loop feedback diagram features a summation junction, where desired output is compared against measured output. The resulting error drives the controller and actuator to force the plant toward the target. However, the required sensor inevitably injects measurement noise into this feedback path. While feeding the output back into the input provides necessary robustness, it mathematically guarantees three persistent engineering hurdles: the risk of dynamic instability, the amplification of measurement noise, and strict physical actuation limits. Control systems engineering is the rigorous mathematical management of these three compromises. This is the closed-loop transfer function, mapping input to output. Notice the mathematics strictly separate the numerator and denominator. Isolating that denominator and setting it to 0 gives the characteristic equation, entirely dictating the system's dynamic behavior. Solving this equation yields specific roots, known in control theory as the closed-loop poles. These poles dictate whether the physical system stabilizes or violently destroys itself in a runaway oscillation. For stability, every closed-loop pole must possess a strictly negative real part, anchoring them permanently in the left half-plane of the complex coordinate system. Stability is never assumed. It is a precarious mathematical state that must be actively engineered into that denominator. To reduce tracking errors and make a physical system respond faster, the standard engineering approach is to tighten the feedback loop by increasing the controller gain, represented by the parameter k. This root locus visually maps pole trajectories as the gain parameter changes, starting at these x marks. Increasing gain pulls the poles outward, altering the transient response. Push gain too high, and they dangerously cross into the right half plane. A high gain feedback loop improves initial tracking performance, but the root locus proves it inevitably risks pushing the system into catastrophic runaway oscillation. Even if a system is perfectly stabilized, it still must fulfill its primary purpose, tracking accuracy. After the transient oscillations decay, the actual physical output must match the reference command. This grid compares system types, defined by the number of pure integrators. A type 0 system forever yields a steady-state error gap to a step input. A type 1 system eliminates step error, but always lags behind a moving ramp. You cannot achieve zero steady-state error merely by turning up a gain dial. It requires structurally integrating the error itself over time. True accuracy is an architectural mandate. This equation calculates tracking error by accounting for the reference command, load disturbances, and measurement noise. To track commands perfectly, we drive the S term, the sensitivity function, towards 0 with high gain, but they are algebraically linked. Driving S to 0 mathematically forces the complementary sensitivity term toward 1. When that complementary term reaches 1, high-frequency measurement noise passes directly into the controller without attenuation. The hardware begins reacting to its own sensor noise. Perfect control is mathematically prohibited. Designing a system to fully reject physical disturbances guarantees the simultaneous amplification of sensor noise. Since minimizing both sensitivity functions simultaneously is an algebraic impossibility, the only solution is to split the compromise across different frequency bands. We engineer the system to maintain high loop gain at low frequencies, to track commands and reject slow physical disturbances. Conversely, we enforce low loop gain at high frequencies to block the rapid, high-speed chatter of sensor noise. This Bode plot is the graphical tool used to verify this frequency domain loop shaping. Notice the downward slope of the magnitude curve across the frequency axis. It confirms the exact transition from high-low frequency gain to the deliberate high-frequency roll-off. Feedback control is the science of placing your compromises at the exact frequencies where they will cause the least physical harm. Even with perfectly optimized frequency math, the physical world imposes hard limits. Actuators have maximum voltages, motors have absolute torque limits, and a valve can only open 100%. Commanding infinite gain mathematically results in actuator saturation physically. The closed loop effectively breaks, leading to severe operational failures like integrator windup, where the controller demands action the hardware simply cannot deliver. We accept the risks of instability and noise because feedback provides a mathematical framework to manage uncertainty, allowing us to align physical reality with our specific commands.